Hello and welcome to our lesson on finding the roots of quadratic equations. Today, we're going to dive into some engaging concepts that will not only enhance your algebraic skills, but also bolster your overall problem-solving abilities in mathematics. In this lesson, we will focus on understanding why and how we find the roots of a quadratic equation. Our primary goals for today are exploring the concept of roots in quadratic equations, understanding the underlying principle behind factorizing quadratics, delving into multiple examples of factorizing quadratics, including its use to simplify fractions. In our previous lessons, we've built solid foundational knowledge by discussing solving linear equations by understanding how to isolate variables and find their values, graphing linear functions via knowing how to plot points and draw the lines representing equations, exponents and polynomial expressions, manipulating and simplifying algebraic expressions. With this foundation, we are now prepared to tackle the roots of quadratic equations. Understanding how to find these roots is crucial because it allows us to solve a variety of real-world problems, such as calculating the trajectory of an object or optimizing profit functions. For instance, imagine you need to determine the points where a ball hits the ground when thrown at an angle. Finding the roots of the quadratic equation representing its path will give you these crucial points. Let's get started! In this unit, we will explore three methods to find roots, precisely which are factorization, quadratic formula, and completing the square. In this lesson, we'll focus on factorization. Let's begin with an example. Consider the quadratic 6x squared plus 5x plus 1. First, let's see what the equation looks like when factorized. We want to express 6x squared plus 5x plus 1 as a product of two binomials. We'll need something like a x plus b times c x plus d, where a, b, c, and d are integers. By expanding a x plus b and c x plus d, we get a x times c x, which equals 2a c x squared, a x times d, which equals a dx, b times cx, which equals b cx, b times d, which equals bd. Combining these, we have acx squared plus ad plus bcx plus bd. Now compare this expanded form to our original equation, which is 6x squared plus 5xx plus 1. ac equals to 6, which is the coefficient of x squared. Next, ad plus bc equals to 5, which is the coefficient of x. Finally, b equals to 1, which is the constant term. This comparison tells us that we need a and c such that ac equals to 6. Next, we need ad plus bc to equal to 5. And then we need b and d such that bd equals to 1. Since we aren't dealing with fractions, b and d must both be 1 or both be minus 1. When we sub these values for b and d, our equations reduce to ac equals to 6, and a plus c equals to 5, or a plus c equals to minus 5. Next, we find the factors of 6 that add up to 5. 6 equals to 2 times 3, or to minus 2 times minus 3. Therefore, a and c must be 2 and 3 or minus 2 and minus 3, depending on our choice of b and d. This gives us two options for the factorized form: 3x plus 1 times 2x plus 1, or minus 3x minus 1 times minus 2x minus 1. Notice how taking the negative values gave an equivalent answer, as should be expected. So we could have just taken the positive values throughout, and it wouldn't matter, as illustrated. It is important to note that factorization is essentially an educated guessing game. Setting up a system of equations is not something you should usually find yourself doing when factorizing, but we went through this to improve your understanding of factorizing. You should also remember that not all quadratics are actually factorizable. For a very simple example of this, consider the quadratic x squared minus 2. Pause the video and convince yourself that x squared minus 2 is not factorizable. Now let's return to our example and find the roots of the equation. We have the factorized equation, 3x plus 1 times 2x plus 1, which equals to 0. For the product to be 0, at least one of the factors must be 0, meaning either 3x plus 1 should equal to 0, or 2x plus 1 should equal to 0. Solving these, we get x equals 2 minus a third, and x equals 2 minus a half. Hence, the roots of the equation 6x squared plus 5x plus 1 are x equals 2 minus a third, and x equals 2 minus a half. If we plot the graph of 6x squared plus 5x plus 1, we'll see that it intersects the x-axis at x equals minus a third and x equals minus a half. This confirms our solutions. The method shown may, however, seem a bit tedious. Fortunately, there are a couple of tricks you could use to factorize quadratics. Let us start with the simpler case where the coefficient of x equals 1. Consider the quadratic equation x squared minus 5x plus 6 equals to 0. To solve this by factoring, we need to express it as a product of two linear terms. We look for two numbers that multiply to 6, the constant term, and add up to negative 5, the coefficient of x. If you consider that the factors of 6 are 1, 2, 3, and 6, you can work out that minus 2 and minus 3 are the two numbers we are looking for. So we can factor the equation as x minus 2 times x minus 3 equals to 0. We can double check our factorization by expanding the brackets. If we multiply the brackets out, we get x squared minus 2x minus 3x plus 6, which simplifies to our original expression of x squared minus 5x plus 6. Next, we set each factor to 0 and solve for x. So x minus 2 equals to 0, or x minus 3 equals to 0. Therefore, x equals to 2 or 3. Let us now examine the more complex case where the coefficient of x squared is not 1. Suppose we have 6x squared plus 13x plus 6 equals 0. First, we start by multiplying coefficient of x squared and the constant together. This gives us 36. Then we want to find two numbers that multiply to give 36 and add up to 13. By examining the factors of 36, we find that 4 times 9 equals to 36 and 4 plus 9 equals to 13. We now rewrite 13x as 4x plus 9x to get 6x squared plus 4x plus 9x plus 6 equals 0. Next, we factorize the first two terms and the last two terms separately. 6x squared and 4x have a common factor of 2x, while 9x and 6 have a common factor of 3. The expression can thus be rewritten as 2x times 3x plus 2, plus 3 times 3x plus 2, which equals to 0. Note that the two brackets are the same, so we can rewrite this as 2x plus 3 times 3x plus 2 equals 0. Next, we set each factor to 0 and solve for x. 2x plus 3 equals 0, or 3x plus 2 equals 0. Therefore, x equals 2 minus 3 over 2, or minus 2 over 3. Let's now touch on another use of factorizing, which is simplifying fractions involving quadratics. When you have a fraction where both the numerator and the denominator are quadratic expressions, you want to factorize both the numerator and the denominator, then cancel out any common factors. As an example, let's consider the fraction x squared plus 3x plus 2 over x squared plus 5x plus 6. Factorizing the numerator, we have x squared plus 3x plus 2 equals x plus 1 times x plus 2. Factorizing the denominator, we have x squared plus 5x plus 6 equals x plus 2 times x plus 3. So we rewrite our fraction as x plus 1 times x plus 2 over x plus 2 times x plus 3. We can cancel out the common factor x plus 2, giving the simplified fraction x plus 1 over x plus 3. We have to be very careful here. This equality does not hold when x equals to minus 2, since the left-hand side is undefined at that point due to the denominator being 0. Accordingly, If this simplification is used in solving an equation, you have to take care not to generate false solutions. For example, if you get x equals 2 minus 2 as a solution to an equation involving the simplification in this example, you'd have to reject that solution since you get undefined expressions in your original equation. Did you know that the method for finding the roots of quadratic equations, including completing the square, dates back to ancient mathematicians like al-Khwarizmi? In the 9th century, al-Khwarizmi, a Persian scholar, developed systematic techniques for solving quadratic equations, which laid the foundation for algebra. These methods were later refined by European mathematicians during the Renaissance, enhancing their precision and application. The principles they developed are still taught and used in mathematics today, showing how timeless and important these mathematical concepts are. In today's lesson, we explored the importance and methods of finding the roots of quadratic equations. We began by understanding why roots are significant, particularly in real-world scenarios, such as determining when a projectile hits the ground. We then reviewed how graphs can provide approximate roots by observing where the graph crosses the x-axis. Moving on to exact methods, we focused on factorisation. We illustrated how to express a quadratic equation as a product of two binomials and solved for the roots by setting each binomial to 0. Through examples, we demonstrated the factorisation process and how to verify the roots by plotting the graph and observing its intersections with the x-axis. We also touched on quadratic fractions, showing how to simplify expressions by factorising both the numerator and the denominator and cancelling common factors. By understanding and applying these methods, we can accurately find the roots of quadratic equations, enhancing our problem-solving skills in algebra and beyond. Watch the rest of the GCSE Maths course at Sophos Education.